Millennium Bridge is a bridge in central London. Why do we treat this bridge in this video? Because it's very interesting from a structural dynamics perspective. It was even called the wobbly bridge and closed after 2 days. Why? Keep watching. Let's start with some general facts. The Millennium Bridge is a suspension bridge, crossing the Thames at central London between Tate Modern Gallery at the south bank and Peters Hill at the north bank, close to the St. Paul's Cathedral. The bridge is a result from a bridge design competition held by Southwark Council in 1996. More than 200 applicants joined, but it was won by Arup, Foster and Partners and Sir Antonio Caro. Construction started at the end of 1998 and the bridge opened at the 10th of June in 2000. Because the suspension bridge is located to the St. Paul's Cathedral, the view to the cathedral is not allowed to be blocked, so the structural height of the bridge is limited. Moreover, the Thames is used by ships, leading to a certain clearance. The result is that only a very limited construction height for the bridge is allowed. The bridge is not only suspended vertically but also laterally. This increased the lateral stiffness of the bridge, leading to an even more slender design of the bridge deck. Therefore, the structural team decided to design a suspension bridge with very low pylons, as you can see on this screen. The bridge has 3 spans, 81 meters north, 144 meters in the middle, and 108 meters at the south. The distance from the top to the cables to the bottom is only 2.3 meters, 6 times as small as comparable suspension bridges. This leads to very high tension forces in the cables, approximately 22.5 meganewtons. The cables are locked coil cables and are connected to the abutments and the piers. The piers are made out of V-shaped steel sections and placed on a concrete section. These sections are founded on caissons 80 meters below the riverbed. The bridge deck is 4 meters wide and is made of aluminium, keeping the dead load of the bridge very low, with only a mass of 2 tons per meter. The bridge is very slender and hence more susceptible to dynamic loads, e.g. wind loads, pedestrian loading, etc. Therefore, wind tunnel tests have been applied in the bridge design phase and the bridge deck is optimized. Using a limited construction depth and round edges for the cross-section at the side of the bridges, as you can see in the cross-section at the bottom of this page. At the opening day, the 10th of June in 2000, 80,000 to 100,000 people make use of the bridge, leading to peak moments of 2,000 people on the bridge at the same time. Due to the large amount of people on the bridge, unexpected movements occurred. The bridge started to vibrate laterally, it's sideways, with a maximum acceleration between 0.2 and 0.25 g, and it had an amplitude of 17 millimeters. People experienced difficulties to walk. What happened? The pedestrians, to help to maintain the balance, they started to walk in phase with the swaying behavior of the bridge. This is called synchronous lateral excitation. The strong lateral response of the bridge was amplified by the motion of the pedestrians, which want to correct the motion to be more stable. This is presented in this figure on this slide. The next day, the 11th of June 2000, the maximum people allowed to walk on the bridge was limited and the bridge was closed on the next day at the 12th of June of 2000. Improvements were needed to regain the level of comfort of the bridge. That means that the lateral accelerations needed to be reduced. Hence, Arup started the investigation to come up with design solutions with 3 goals. The first one was the prediction of the behavior of the bridge, including the large amount of people on the bridge. The second goal was the determination of the magnitude of the lateral forces, and the last one, the development of the measurements to restrict lateral movements. How to solve the problem? Again, Arup came up with 3 solutions, and the first one is regarding the stiffness of the bridge. The angular frequency of the bridge is 0.5 Hz at the main span, but the lateral motions caused by the lateral synchronous excitations is 1.3 Hz. This means that the first lateral eigenfrequency of the bridge should lay above 1.5 Hz. And this means that the eigenfrequency of the bridge should be 3 times as high as its original frequency. An increase of the eigenfrequency with a factor 3 requires an increase in the stiffness with factor 9. This is impossible to achieve without drastically altering the slender design of the bridge. Moreover, keep in mind, as already mentioned, that the allowed construction height is limited. The second solution was to limit the amount of people allowed to walk on the bridge, which was not an option. The last measurement or solution was the increase of damping, which will limit the acceleration of the bridge. There were 3 different methods. The first one is the incorporation of tuned mass dampers, which you can see in the picture above. In the picture in the middle, you can see the application of viscoelastic dampers and below active control. The tuned mass dampers were chosen to limit the lateral motions, and also, in addition, viscoelastic dampers have been installed to limit the vertical motions too. I will make more videos in which I will explain in detail the principles of the ideas of these damping stuff, because it can be quite complicated otherwise, and this video will then take too much time. So keep subscribed and keep be updated. The bridge reopened at the 27th of February in 2002, and the measurements taken proved to be working. What can we learn? The lateral vibrations have been detected already in other bridges too, but it was not implemented in the design of the Millennium Bridge. This should be done in the design of this bridge. And the experiences which were obtained in the design and use phase of the Millennium Bridge can be used for other slanted structures as well.